boron molecule, the next homonuclear diatomic molecule, which will now include the p orbitals. A single boron atom has 5 electrons. The configuration is 1s2, 2s2, 2p1. In this configuration, now since the p orbital is being involved, I'll show you how actually this molecular orbitals would be formed. As I said, two atomic orbitals could undergo linear combination and thereby produces two molecular orbital. One is additive, that is psi A plus psi B, which is also known as bonding molecular orbital. Another is subtractive, that is psi A minus psi B, discussed in last class. This is the anti-bonding molecular orbital. The bonding molecular orbital is of lower energy, greater stability. Anti-bonding one is of higher energy than any of the atomic orbitals and of course with lower stability. The electrons are being filled up preferably to the bonding, and the electrons present in anti-bonding actually counters or challenges the bonding and thereby lowers the bond order. Now, since p orbitals are involved, as we know, the p is having px, py and pz. All these are projected along the three axes. So this 3p orbitals of one boron and another 3p orbitals of another second boron will actually involve the mixing of 6 atomic orbitals. The 6 atomic orbitals will result in the formation of course, 6 molecular orbitals. Within the 6 molecular orbitals, 3 will be bonding molecular orbital and 3 will be anti-bonding molecular orbital. Out of this 3 bonding molecular orbital and 3 anti-bonding molecular orbital, as I said, along the internuclear axis, the molecular orbital so formed is known as sigma molecular orbital, and that is perpendicular to the internuclear axis. Above and below to the internuclear axis is pi molecular orbital. So since only one sigma bond is formed, out of this 3 bonding molecular orbital, one will be sigma bonding molecular orbital and 2 will be pi bonding molecular orbital. Similarly, in anti-bonding also, we will have one anti-bonding molecular orbital, that will be sigma, and 2 anti-bonding molecular orbital, that will also be pi. So as a whole, we are having, out of the 6 molecular orbitals, we are having 3 bonding, 3 anti-bonding. This 3 bonding molecular orbital will also be 1 sigma, 2 pi, and 3 anti-bonding molecular orbital also, there will be 1 sigma and 2 pi. So ultimately we are having 1 sigma bonding molecular orbital, 2 pi bonding molecular orbitals, 1 sigma anti-bonding molecular orbitals and 2 pi anti-bonding molecular orbitals. Thereby how the 6 molecular orbitals are made. Of course, I did not make this according to the energy diagram because I just shown how the orbitals are present, and now I am showing the energy diagram. Of course, the anti-bonding one will have higher energy and bonding will have a lower energy. Now, in this energy diagram, molecular orbital diagram, we will make the boron atoms as this is our energy, This stands for 1s. This stands for 2s. This stands for 2p. Of course, in this we have px, py and pz. Let's fill the electrons over here. 2, 2 and 1. That is 1 is 2, 2 is 2 and 2p1. This is our linear combination of atomic orbital or boron molecule. 1s and 1s atomic orbitals would form two molecular orbitals. One will be of lower energy, another will be of higher energy. This is sigma bonding molecular orbital or sigma 1s, and this is higher one is sigma anti-bonding or sigma star 1s. This is sigma 1s, this is sigma star 1s. Similarly, 2s will also form two bonding molecular orbital, one bonding and one anti-bonding molecular orbital. This is sigma 2s, the bonding molecular orbital, lower energy. This is sigma star 2s. This we have seen till beryllium. Now, the p orbitals, keep one point in mind, that the atom with atomic number less than equal to 7, that is till nitrogen, or in molecule it is double, less than equal to 14, we will have certain other rule, and beyond 14 again we will have certain different rule. So let's first make the rule. After that I'll explain why this has happened. So now till boron, carbon and nitrogen, we will have first the pi bonding molecular orbital. This is 2px, 2py, pi bonding molecular orbital, pi, and this is r, sigma 2px, 2pz, sorry, z is internuclear axis. These are the bonding molecular orbitals. Lower energy of this pi will be of lower energy than sigma for boron, carbon and nitrogen. Here we will now have anti-bonding pi, and anti-bonding sigma will always have a higher energy level than anti-bonding pi energy level. So this is known as pi star 2px, pi star 2py and sigma star 2pz. That's how all 10 molecular orbitals are being formed. The filling up of electrons in molecular orbitals do follow the Aufbau principle, Pauli's exclusion principle and Hund's rule. Thereby the 5, 5, 10 electrons would be filled as 2 over here, 2 in anti-bonding, again 2, again 2, and since these 2 are degenerate, that is orbitals with same energy, single electrons would occupy like this. So it would have a molecular orbital configuration. Sigma 1 is 2, sigma star 1 is 2, sigma 2 is 2, sigma star 2 is 2, pi 2px 1, pi 2py 1. Rest all molecular orbitals would be present, but none of them will have electrons. They would be vacant. The molecular orbital diagram would be, and these 2 are degenerate. So 2, now we are having 10 electrons filled. Of this is our bonding molecular orbital. This is also bonding molecular orbital, and these two are bonding molecular orbital. Of this, only these two are anti-bonding molecular orbital over here, that is filled with electrons. It means if we have the bond order to be calculated, as the bond order comes equal to half into number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital. In bonding molecular orbital, we have 2, 2 and 1 and 1 means 6, and anti-bonding we have 4. So as a whole, the bond order comes equal to 1. One more very important thing is, boron contains, B2 molecule contains 2 unpaired electrons. That is, number of unpaired electrons are 2. Hence, it will be paramagnetic. That is, it will be deflected when placed in an external magnetic field. And the spin only magnetic moment is equal to square root of n into n plus 2. Now, let me explain this magnetic moment once. Since electrons are charged particle, and we know whenever a charged particle swings or spins, whether in clockwise or anti-clockwise direction, that is, whenever a charged particle is in motion, it induces a magnetic field. The direction of this induced magnetic field depends upon the direction of the motion of electrons. In fact, electrons are having two types of motion. One is spinning clockwise or anti-clockwise, represented by plus half or minus half, the spin quantum number. Another is its motion round the nucleus, that is, its motion in the orbital. For certain species, up till atomic number 30, that is till the first transition series or 3D series, we have the orbital contribution of magnetic moment very, very less or negligible. Therefore, we only consider the magnetic moment that is occurred through the spin of electron or clockwise and anti-clockwise movement of electron. When the two paired electrons are there, the north-south induced magnetic field is definitely cancelled by the paired one. But when an unpaired electron is present, it creates a magnetic domain which is non-zero. This magnetic domain or non-zero magnetic moment is actually responsible for spin only magnetic moment, which is represented by square root of n into n plus 2 Bohr magneton. The unit is Bohr magneton, where n is the number of unpaired electrons. So here the spin only magnetic moment will be square root of 2 into 2 plus 2, or that is equal to square root of 8, or that is nearly equal to 2.8 Bohr magneton. So that is the reason why boron is diamagnetic and its bond is equivalent to a single bond. Now we'll come to next the carbon.